orientation. There's a million ways that you can get something that's equivalent to that state. And so the correlation is that formation of the activated complex requires a decrease in the entropy on some level. This isn't necessarily going to be exact for all systems. It's probably going to be a function of the exact contributions to entropy for the systems. But I think that's safe to say for ionic systems in solution. High order, low order, right? And so, high order, low order. Just because I say it doesn't mean that's what I meant to say. Remember that. So delta S for this guy is going to be negative. And so depending on the magnitude of delta S, it'll be a more negative delta S than others, right? The higher the order in this state, the higher the change in entropy that's required to get to the interacting state, the smaller your A value is going to be. Yeah? And so this serves to, the same way that the collision frequency calculated the probability, it associated the probability that with which two systems or two molecules are going to collide, this delta S takes that probability, but now it casts it in terms of an entropy. It said, instead of saying, we got this collision frequency, and what's the probability of having a collision? Instead, now our new expression is saying, what's the probability of forming this low entropy or state? And the higher the delta S, the more negative the delta S, the smaller this whole blob of constants becomes. Considering that a reaction that requires a specific orientation, that interaction with in that specific orientation is even higher in order. It's a more highly ordered interaction. Then delta S will be even more negative for a system that requires a specific orientational factor, right? A specific orientation of collision. Does that make sense? All right. So basically, we just turned the gas phase thing that said collision frequency times probability that the thing happens with the appropriate energy into an expression that says probability of achieving a low entropy state, a low entropy state times the same energetic probability, right? The same factors. Some of these notes have to be edited. I'm going to post these, but there's some things that aren't exact. And at this point, you're probably not, on it enough to know where I've made mistakes. But in case you do find my mistakes, just know that I admitted that there were maybe possibly errors in these notes ahead of time. We're gonna try to look at a relationship between the K values, the rate constants, and the equilibrium constant for a specific reaction. And it turns out that in the limit of dilute solution, the ratio of the rate constants is equal to the K to Q value. This is not necessarily the case for more concentrated solutions, but it works well in dilute solutions. This ends up being very important because the connection between the rate constants and the equilibrium constants allows you to calculate one value in terms of the other. So let's take a look at this real quick here. Take a reaction, A plus B reaches equilibrium with C. And if this is if this is if it proceeds in a bimolecular, if the forward rate depends specifically on collision between 1A and 1B and there's no other intermediates formed, then we can say that K forward is conc A times conc B, right? If the reverse reaction is unimolecular and only one C molecule is required to decompose, then the reverse reaction is Kr times C. So we set those two equal to each other at equilibrium, we take ratios, and we get that Kf over Kr is conc C over conc A times conc B, right? And that has the same exact form as our equilibrium constant. Our equilibrium constant for this reaction would be the activity coefficient times the concentrations. If we set all of these activity coefficients to 1, then the two are equivalent, right? So in dilute solution, we know that the activity coefficients for a solute are equal to 1. We talked about that in that 20-page thing about activities that we looked at. So take-home message, there is a relationship between the equilibrium constant and the rate constants for a reaction. I was going to try to show you some calculations for determining one from the other, but we're just not going to have time this time through. Okay, so we talked about what did we talk about? We talked about how the Boltzmann distribution of energies can be used to discuss the effect of an increase or change in temperature on the equilibrium constant of the reaction, right? Specifically, we said that for an endothermic reaction, the products are higher in energy than the reactants, and so if we increase the energy of the system, we shift the equilibrium towards the higher energy species just because we've got more energy to store, and we got to store it somehow, and so the fact that we've got a rapid equilibrium means that we can store some of that energy by increasing the concentration of the higher energy species. And then we also derived an equation using I think it's the Van Hoff equation, relating the delta H of a reaction to the dependence of K on temperature. And the Van Hoff equation said the same thing, basically, that an increase in temperature will increase the products for an endothermic reaction, and it'll increase the reactants for an endothermic reaction. We already made that correlation a couple times. The relationship between the equilibrium constant and the rate constants gives us another system, or another model that derives the same conclusions, that results in the same conclusions. Specifically, referring back to that natural log of K over T graph that Arrhenius put together, the slope of that graph was proportional to the activation energy, the energy requirement for the system, right? And if you look at a given reaction, the activation energies are going to be different for the forward direction and the reverse direction, right? Therefore, the value of K, the dependence of the value of K on temperature will be different for the forward direction and the reverse direction. Yeah? So that's related by the slopes. Something with a higher activation energy is going to have a higher negative slope. Something with a lower activation energy is going to have a lower negative slope. And depending on what the relative slopes are and what the change in temperature is, equilibrium will shift in the appropriate direction with a change in temperature. So let's look at this. As you go to 0 on this graph, that's implying an increase in temperature, right? And you look at the slope here for the activation energy, or the activation energy of the forward reaction, and K increases greatly for this forward reaction, with a given increase of t, movement towards 0 on the x-axis. The magnitude of k increases more for, in this case, the reactants than it does for the products, because the reactants have a higher activation energy. So what we're saying is that because k for the forward direction becomes larger with an increase in temperature, the rate in the forward direction becomes larger for an increase in temperature. Yeah? And if the rate for the forward direction grows more rapidly than the rate for the reverse direction, equilibrium has shifted to the forward direction. Therefore, the higher energy products are going to be favored with an increase in temperature. In this case, that the products are, the forward direction for formation of the products increases with temperature in the case that the products are higher in energy. And similarly, if that was the reverse reaction, we had the inverse relationship between the slope of the forward direction and the reverse direction, then inverse effects would be observed. Yeah? So it's just another way of looking at that whole temperature dependence on equilibrium thing that we looked at earlier. Okay, so the way that we're going to do this, your book actually approaches this in kind of a different order than I'm going to approach it here. But essentially, if a rate expression can, or if an appropriate mechanism can be found for a reaction, its rate law can be cast in terms of the reaction constants, the rate constants for each. I call them, in this I use the language discrete step, but in your text they probably use the term elementary step. So if you can describe a reaction mechanism that uses specific elementary steps to move from products to reactants, then you can write a rate expression for that system that casts the rate of the reaction in terms of the energy requirements on each of those elementary steps, the energy requirements of the steps that are involved in that reaction. In general, the way that the way that rate laws are, the way that reaction mechanisms are obtained is to look at the exact form of the rate law that's determined experimentally. And so your rate law is always cast in terms of concentration. It's K for that reaction times concentrations of products raised to, reactants raised to the power of some coefficient. Your rate law always has that form. This coefficient cannot be determined by just the chemical equation. If the chemical equation, if the actual reaction mechanism follows the chemical equation explicitly, for instance, one of the guys that we're going to be looking at here is reaction of NO plus O2 to form 2NO2. If this all happened in one step, if two NO molecules and one oxygen molecule came together and collided, then the rate would be proportional to each of these concentrations raised to the power of their coefficient. So the rate would go as K times conc NO to the second power times conc O2 to the first power. That would be your rate expression, right? It's very unlikely to have termolecular interactions. Statistically, it's just very improbable in space that three molecules are all going to collide at the same time. What's more likely is that one molecule collides with another one and they form some intermediate, and then that intermediate goes on in a subsequent collision to move on to the next stage of the reaction. Maybe that's products, maybe it's another intermediate. But suffice to say, these intermolecular interactions are very unlikely, and therefore higher order reactions, where like 4 things come together in one collision and react, those are very highly unlikely. And so you can't figure out, it's very difficult to figure out the rate law just by looking at the reaction equation. It's something that you end up doing by calculation. And we've seen these calculations all the time. What do we do in Gen Chem? We take a reaction and we hold one of the concentrations constant while changing the other one, and we see how the rate changes. And and based on what happens to the rate, we can figure out what the coefficient was in front of that concentration. For instance, if the concentration is 1 and on O2, and we hold NO constant, if we double the concentration of O2, the rate should double. But if the exponent here on O2 is 2, and we double the concentration of O2, the rate would quadruple. And so there's those mechanisms, and there's some others that we'll talk about on Thursday for determining the absolute rate law. But suffice to say, the rate law it's very difficult to determine just by looking at the reaction, unless it's a very, very, very simple reaction mechanism. In very simple reaction mechanisms, sometimes the rate law matches that predicted by the equation very closely. So what we're going to do right now is we're going to look at the way to derive these integrated rate expressions for very simple mechanisms, and then we're going to extend that and look at some more complicated mechanisms and how to write rate laws for those mechanisms. So in a very simple unimolecular decay reaction, like what would happen with a nuclear process, nuclear decay, you have the rate being proportional to the concentration of whatever the species is that's decaying. Sometimes. In that case, we can write the rate of the formation of products, and generally when we write a rate expression, we're talking about the rate in terms of the formation of products. We can say that that's equal to the negative rate of the change in concentration of A with respect to time, right? So the rate at which products are formed is negative dA over dt for this guy because of the stoichiometry. And because this elementary step is proportional to the concentration of A to the first power, since there's only one A required to make this reaction happen, we can write this statement that negative dA over dt is equal to K times A. This guy, we just move the appropriate variables to the appropriate sides of the equation. If this is dA, then we're going to move conc A over here. We're going to put the dt over here, and we're going to integrate both of these expressions between the appropriate limits. And the result is going to give us an expression that will allow us to cast the absolute concentration of A or products, for that matter, with respect to time. You integrate this, you integrate dA over A from A naught, whatever the initial concentration of A is, to A final. And you integrate the Kf dt from the initial state, which is usually 0, up to T final. And you get this expression here, natural log of A final over A initial is negative K times T. And just moving, raising B both to the power of E, you get that A final over A initial is equal to E to the negative KT. Yeah? This can be rearranged, and we've got that the concentration of A at any given time for this reaction is A naught times E to the negative KT. So this expression will give you, that'll give you the concentration of A, and if you use the reaction stoichiometry to relate the concentration of A to the concentration of products, if there's a 1-to-1 ratio between A and products, then the concentration of products as a function of time is just A naught minus A final, right? If there's a 1-to-1 stoichiometry. Anyway, so suffice to say, you can take this integrated rate expression for a very simple mechanism, and you can derive an expression that gives reactant concentrations as a function of time. Speaking of time. So here's another reaction, and this is a simple mechanism, but these things get fairly complex fairly quickly. So in this one, we've got a unimolecular reaction in the forward direction, but we also have a reverse reaction. Now oftentimes there are reverse reactions that, that can be approximated as being negligible, in which case we wouldn't draw this equilibrium. But in this case we're going to account for the equilibrium, and we're going to say that the rate at which A is consumed is going to be proportional to the, right now we're going to start using prime to indicate the reverse rate constant and the unprimed K to indicate the forward rate constant. So the rate at which A is consumed, or the rate of the reaction is negative dA over dt. The rate at which A is consumed is going to be K times A minus K times B, K prime times B, right? Because B is able to convert back to A. And so if you're looking at rate of change of A, you have to incorporate both of those expressions. We look at the reaction stoichiometry for this particular reaction, and there's a one-to-one relationship between A and B. And so the reaction stoichiometry allows us to cast the concentration of B in terms of the initial concentration of A and whatever the actual concentration of A is at any given moment in time. So conc B is equal to conc A naught minus A. You plug this expression in for B, and you get this guy here. This guy, this expression, turns into that expression. And then we have to get a new page. This thing. We integrate that expression, and I'm not going to ask you to integrate it. It's, I don't even think they integrate it in your text. They might. They integrate this thing by hand in some other text. It's actually, these expressions get very difficult to integrate by hand as you move on. But you integrate those concentrations, those rate terms that we had on the last page, and you end up with terms like this. And so, as with the unimolecular decay reaction, we can derive expressions that relate the concentrations of the species with respect to time by integrating that rate expression that we generated. And for this guy, it ends up looking like that. I put this in here. I want you guys to integrate this one by yourselves. It's not such a hard integration. In here, we've got 2 A molecules going on to form products. We're going to assume that the products do not decay back to reactants in this case. And this is one of those cases where we're making an assumption here that might not be true for every mechanism. For a mechanism where there is a relevant magnitude back reaction, we'd have to draw an equilibrium arrow here, and then we'd have to cast the rate expression in terms of the forward and reverse directions. We're not going to do that right now. We're just going to assume that it only moves in one direction. In that case, you can say that the rate at which products are formed is negative dA over dt times 1/2, right? Because one product molecule is formed for every 2 A molecules that get consumed. And we know that the rate of the forward direction is whatever the forward rate constant is times the concentration of A squared. So you notice that here we are writing the coefficients in front of the reactants based on how many of them have to collide. And that's the difference between looking at an overall reaction and looking at an elementary step. For an elementary step, it's absolutely safe to say that the rate goes as K times the concentrations of things involved in that step. But when you move on to an overall reaction, you don't necessarily know which steps are which, or how many, you don't know what the mechanism is necessarily, or what the elementary steps are going to be. And so you can't just simply raise the particular reactant to a power of the coefficient in the balanced equation. You can only do that for elementary steps. In this reaction, we're assuming that there's only one elementary step, and that's two A molecules going on to form products. So we say rate is negative 1/2 dA over dt is equal to K times A squared. You're just going to isolate the appropriate variables. So A squared is over here, you're going to move it down here into the denominator. You're going to move that dt over in front of the K like we did last time. And you do what you want with the two, I don't care. And then you're going to integrate that between the appropriate limits. Concentration will go from A naught to whatever A final is, and time is going to go from 0 to whatever the final time is on that integration. And so you integrate that. I want you guys to do it for the sake of your own practice, but you should get this answer that 1 over A is equal to 1 over A naught times 2 KT. Yeah? If I said everything that was on my mind, you people would get rid of me. I don't know what that means either. All right. I just forgot what the hell you made me say that. That's funny. So, here's an example for you. This one, don't expect that you're going to have to do this. I put a few mechanisms in here because I wanted to illustrate to you how complicated this gets as you make the reaction mechanism more complicated. So, for this guy, we've got A and B molecules. We're going to assume that it only goes in one direction. There's no equilibrium, and so we're not going to account for a back reaction. We cast it in terms of the elementary interaction between A and B molecules, and we say that the rate of product formation is equal to negative dA over dt, because there's a one-to-one stoichiometry between A and products. And we're going to say that that's equal to the K of the forward rate, or the K of the forward rate constant, or the forward rate constant times the concentrations of A and B raised to the first power. To obtain the integrated rate expressions for this guy, we're going to cast both the concentration of A and B in terms of X, where X is a measure of the progress of the reaction. So we say that conc A is conc A naught minus X, and if X moles of A have been consumed, then therefore the one-to-one stoichiometry between A and B suggests that X moles of B have been consumed. And so we get B is B naught minus X. We're going to take dA and say if A is A naught minus X, then dA over dt is the d over dt of the constant, which is 0, minus dx over dt, right? And so dA can be cast as negative dx, right? I threw t in there, but it's all the same. So you take this expression and you integrate from x equals 0 up to x on this one side. On the other side, you do that same kdt thing and integrate from 0 up to whatever the final time is. And you get this expression here, which is pretty difficult to integrate, but it can be recast by removing the A naught and the B naught, or there's 1 over A naught B naught term to the outside and multiplying it by that inside term. This guy is easier to integrate because we've got x to the first power in the denominator of these guys. And so you integrate these two expressions from 0 up to x, both of these up to 0, from 0 up to x, and then you integrate kdt from 0 up to t. I think you might have having to integrate that in a homework, maybe not. And you end up with this expression down here. Natural log of A over B is equal to natural log of A naught over B naught plus A naught minus B naught KT. So again, by determining the specific elementary steps in a mechanism, and then casting the rate law in terms of those steps, and then integrating that rate law, we come up with an expression that gives us the concentrations of any reactant or product as a function of time. Yeah? And that's kind of the take-home message of this whole section in kinetics. figure out what your action is, express it in the terms of a series of elementary steps to write a rate law, and then integrate those rate laws between the appropriate limits, and you'll have an expression that gives you concentration of, whatever species as a function of time.